Hey, Calculus, Mr. Florio. We're going to look at a couple more examples from this section. The majority of the section is just applying that mean value, the fundamental theorem of calculus. And then I'm going to talk about a couple other things coming from that. But the couple of things we're going to talk about, there's not going to be a lot on your homework with these questions. It's just kind of good to see once. The mean value theorem of integrals, if you remember just the mean value theorem, not for integrals, if you have some curve on some interval from A to B, what the mean value theorem said is if you take the average rate of change in that interval, which would be the slope between the endpoints, let me draw that a little bit better. Let's put it up here. There's got to be somewhere in this interval, if the function is continuous and differentiable, somewhere in this interval, the slope at the derivative at a specific point is going to be the same slope as the slope of this average rate of change between the two endpoints. So like right here, maybe it looks to be where the slope at this point matches the slope of the average rate of change of the whole interval. And it actually does, it happens at least one place, but it actually looks like it happens at two places, where at these two places, the derivative at a specific point matches the derivative or the average rate of change of the whole interval, the slope between the two endpoints. So applying that, so that's just the mean value theorem. The mean value theorem of integrals is kind of the same idea. If I want the area under a curve, well, the area, the smallest rectangle, if I take the smallest point in that interval, is going to undershoot the area. If I take a rectangle that goes through the maximum of that interval, it's going to overshoot the area. There's somewhere in the middle where if I take just the area of this rectangle, that rectangle will be the exact area under the curve. And in this case, it's almost like I overshot right here, but then I undershot right here. So it's almost like taking that chunk and moving it right here. And this rectangle will be the exact area of this curve. And if the function's nice and continuous and integrable, that's going to happen. There's got to be some point between A and B where if I take the area of that rectangle, that's going to be the exact area as the area under the curve, even though the curve is in a rectangle. You can kind of like condense it into one, like cut it up and make it into a rectangle. That value where this happens, so if that's C, this would be like f of C. That's what we call the average value, or the mean value, the average value in that interval. So the mean value theorem for integrals is that if the function is continuous and there's a number C in the closed interval such that then there exists a number C in the closed interval of A and B such that the area under the curve is equal to the average value times B minus A. That's just the width. So the height of this rectangle is f of C, and the width is from A to B. That's just B minus A, right? Subtraction tells you the distance from A to B. So if I take the base times the height, that's going to give me the area of the rectangle, which is going to be the exact area under the curve, because you can kind of take a curve and sort of force it into a rectangle. If you divide both sides by B minus A, alternatively, you see this formula sometimes written as 1 over B minus A. So just divide both sides by B minus A, and you get the B minus A on the left side. The integral from A to B of f of x equals f of c. So that's just dividing B minus A on both sides. They cancel out over here, and then you get the 1 over B minus A over here. So that is what we call the average value again, the average value of the function in that interval. So we're going to find that average value in this example coming up here. So find the average value of the function 3x squared minus 2x on the interval 1 to 4. So we can graph it and stuff, but I'm just going to do it out. So I want to find f of c, which is the average value, and that's just 1 minus b minus a times the integral from a to b of f of x, which is this, dx. So I have some function. The average value is going to be the area divided by the width of the interval. And let's see. So this is going to be 1 over. So if this is my a and b, it's going to be the width of the interval is a 3, 4 minus 1. Okay, so that's 1/3 times, let's see. The antiderivative is going to be 3x cubed over 3 minus 2x squared over 2 from 1 to 4. And those 3's are going to cancel out, and those 2's are going to cancel out, so it's going to be 1/3 times, let's see, x cubed minus x squared. So if I plug in 4, that's 4 cubed minus 4 squared. Put another parenthesis here. Minus, if I plug in 1, that's going to be 1 cubed minus 1 squared. So again, here's like my f of b minus f of a. And when I do that, I just got to plug 1/3 into that at the end. So let's see, 4 cubed is 64, 4 squared is 16, minus, that's 1 minus 1, which is 0. So 64 minus 16 is 48. 48 over 3 is 16. So that's what f of c is. The average value, the average height of this function is 16. So if I did base times height, 16 being the height and the base being the width, which is the width is 3. 60 times 3 will give me that area under the function, which is 48. Anyways, so the average value of the function is 16. You could find where that value is by plugging it in. So if I want to find that c value, if f of c equals 16, so 3c squared minus 2c equals 16, I would just, to solve this for c, set it equal to 0. You could maybe be able to factor it, but I'm going to use the quadratic formula. And the c values where this happens ends up being at -2 and 8/3 if I wanted to find the c value where it occurs. So this is the average value. It's found at these two points, and that's the average value of a function. That's the mean value theorem of integrals. We're going to skip this example. And I'm just going to talk about this real quick. There's not much to say. If your limits of integration is a function, like instead of going from 0 to 1, going from 0 to x, where x can be any number, it's a different variable than the function I'm taking the derivative of. So my function capital F of x is a function of x, and x is going to be a function of the antiderivative of cosine of t, which the antiderivative of cosine is sine. And that's from t goes from 0 to x. So that's going to be sine of x minus sine of 0. And sine of 0 is 0, so this is really just sine of x. So f of x is just sine of x. And so what would f of 0 be? Well, that would be just sine of 0, which equals 0. The area from 0 to 0, of course, if you're not going anywhere, your area is going to be 0. If I wanted the area from 0 to pi over 6, then that's really just going to be sine of pi over 6, which is 1/2. At x equals pi over 4, well, it's right up here. F over pi over 4 is root 2 over 2. When x is pi over 3, f of pi over 3 is root 3 over 2. And when x is pi over 2, f of pi over 2 is 1. So the area here is 1. The area over here is half of root 3. The area here is half of root 2, etc. So you can write the limits of integration as a function. So it's not a constant, but it's an actual function. And that's okay. And the reason why I'm bringing that up is just the second fundamental theorem of calculus. We're not going to talk much about this, but it's a big deal because what this is saying is if I take the derivative of an integral, you can almost think of it as like the derivative and the antiderivative cancel out, and you just get f of x. It's pretty interesting because, addition undoes multiplication, addition undoes subtraction, multiplication undoes division, and by chance, I guess, or maybe not by chance, but the differentiation undoes integration. They're kind of like inverse functions, but they weren't studied like that. They were studied as two separate operations, and it just happened to work out that they're almost the inverses of each other. And the reason why this works out is because if I take the antiderivative or the definite integral of that function, that would be using the fundamental theorem of calculus, f of x minus f of a. And I took the derivative of this. The derivative of f of a, that's a constant. That's just going to be 0. And the derivative of capital F is what we call little f. So it makes sense that this f of x really does come out of that. So if I wanted to evaluate the derivative of the integral from 0 to x of this function, you could think of it as like the derivative and the integral cancel out, and it's just going to be the square root of x squared plus 1. It doesn't seem like much is going on there, but they could make this a little trickier. And if you guys take Calc 2, this might be from 0 to x squared or 0 to x cubed, or 0 to e to the x. And how does that change things? So I just wanted you to be aware that it exists, but you're not going to see a ton of questions like that on the homework. All right, that's it.